Okay, so far in this class, we have derived the wave equation and we have solved it in some pretty simple situations. And now today we're going to solve it in a more realistic setting, an ocean waveguide. And before we do that, I just want to put some context behind everything we've done so far, right? So the first thing that we did is we looked at a source in free space. We solved the wave equation. We said P of R was something like, it went as e to the I k dot R, right? And then we looked at what happens when you put a hard bottom but no surface, just to look at the idea of a reflection coefficient. But then we looked, the next sort of most ocean-like thing is we looked at, okay, a source, not in free space, there's a surface there. What happens to the sound as it reflects off that surface? We came up with this idea of, having some imaginary image source here to satisfy the pressure release boundary condition. And in that case, we had this sort of e to the I k dot R, and then this reflection coefficient of -1. So we had something that looked like this. And then, of course, we worked through and came up with Lloyd's mirror. And sort of the next thing we want to do then is we want that pressure release boundary system for the surface, and we want some sort of bottom condition. We want to put a source in there, and we want to find the solution that deals with both the pressure release and the bottom boundary condition. But before we do that, I just want to put some context in these measurements. How do we look at these measurements and make sense of them, right? So this is obviously a complex number. And so a lot of the times I've talked about, in our practical lecture, we talked about computing something akin to the power, right? So the absolute value squared, or the pressure times the conjugate of the pressure, which is going to be all real value. And so this is kind of a proxy for power here. I don't have the right normalization or anything like that, but this is something we looked at, like the intensity. Actually, it's proportional to the intensity, and that allows us to look at how does this thing decay in range. It really allows you to draw diagrams like this, and for instance, for Lloyd's mirror, we had something like that, and this is range, and that's really telling you about how the power decreases with range, or the intensity decreases with range, right? But that's chucking some information, right? We're getting rid of some information when we do that. So the question is really, when we're doing these simulations, we're not just simulating what the amplitude of the field is everywhere, but we're also simulating what the phase of the wave is at that point as well, and at that frequency. So that's what that imaginary part is, and it's good to keep that in mind as we go forward. For now, we're mostly going to look at that pressure as a function of range, and we'll talk about transmission loss. But in the future, we're going to use some of that phase information and use it, exploit it to verify our models against data. Okay. So let's go to where we're at now, right? We want a waveguide that has a surface and a bottom. And one of the ways we can do that very simply is to talk about the idealized waveguide. Ideal. How do we make it ideal? Well, we make the boundary conditions very simple. So let's do a pressure release at the surface, pressure release at the bottom. We're going to place a source at the origin. Okay? We're going to say that the environment is axially symmetric around this origin. So that keeps things simple. We don't have to worry about that third dimension. And we're going to say that the bottom is flat, the surface is flat. So this is a range independent environment. And we're going to put our receiver somewhere out here. Receiver at R and Z. And so now we just need to follow our recipe, and our recipe is to write the wave equation down and solve the wave equation. And so, very simple at this point, but that's kind of like if I just told you make a lasagna, and that's that. But let's start there. So the wave equation, well, We know how to do that. I'm sure you can barely stop yourself from writing it down as soon as I say it. And then on the right-hand side, we're going to have a source that has some magnitude q, and we're going to make it an impulsive source. So the source is positioned at r0. We already said that r0 is going to be equal to 0 z prime. And it's impulsive in the sense that it's just going to happen. It's just going to be totally impulsive in time. Okay? Okay, so now I'm going to add a few pages here. So we have our geometry set up. We have our wave equation written down. So what's the first thing we do? Well, we know we want to take care of that derivative. We can take care of the time derivative and go to the Helmholtz equation. So Fourier transform from time to frequency, and that's going to give us the Helmholtz equation. And the beauty of that is that the second derivative in time is going to become an omega squared, right? Minus omega squared. So now our Helmholtz equation is nice. And then on the right-hand side, that delta t that we had is just going to become 1, okay? Because by definition. So what have we done here? Well, we've said that, first of all, the Fourier transform of P, the pressure field in time is now going to be psi omega, and that's just the pressure field in the frequency domain. We can get, if we compute that, we can get back to the time domain by using inverse Fourier transform. So our solution psi omega would be as satisfactory for us as a solution for P, let's just say, okay? K, of course, is equal to omega over c, and that's why we have this nice k squared here. Okay, and now we're in cylindrical coordinates, right? Because of our axially symmetric ocean. In cylindrical coordinates, so that spatial derivative has an r part, which we know looks like 1 over r d by dr, r d by dr, right? That's the second order derivative when we spatial second order derivative in range. And it has a z part, which is just regular old d squared by dz squared. Okay, and then there's no phi part. Phi would be the actual derivative because we've assumed symmetry. And then we have our k squared term here. And since we're at the origin, this becomes delta r over pi times r, right? Another, which transforms coordinate systems. And then we're going to have delta z minus z prime, okay? Our boundary conditions. Equals 0 at z equals 0, and psi omega equals 0 at z equals h. The depth of the channel is h, by the way. I probably didn't write that in the last slide, but we won't worry about it. Okay, so our whole name of the game here is to keep dealing with these second order derivatives, right? We want to deal with these second order derivatives using transforms, okay? So the first one that we've already dealt with, we used the Fourier transform. Let's deal with these other ones. And we're going to start off by dealing with our second order derivative in range, okay? And so we're going to deal with these two remaining blue transforms and transform this equation into an algebraic equation. So let's write that down. Our recipe is getting a little bit more detailed. It's like you got to fry up a bunch of vegetables before you make lasagna first. So we're going to do that. And then we're getting closer to something real in terms of a recipe. So transform into algebraic equation. And the first thing we're going to do that is we're going to use the Hankel transform. With respect to range, and our transform variable is going to be kr, okay? And so just like we had a Fourier transform that's based off of trigonometric functions, now we're going to have the Hankel transform, which is based off of Hankel functions, or Bessel functions, combinations of Bessel functions, basically. Okay, so our new transform variable, we're going to say this is our Hankel transform of psi omega. Now we're just going to keep track of our transforms with subscripts. Is going to be psi omega kr. So psi omega kr. Now the definition, okay? R times psi omega, and then Bessel function, 0th order, kr dr. There you go, okay? And I'll just put by definition in case you you worried that I just came up with this, you know, somewhere and whatever. Okay. And the inverse, well, to get back to psi omega, the inverse should have some symmetry, and it's very symmetrical in this case, just like the Fourier transform. With the same Bessel function, same argument, we're just changing what we're integrating over. So this is going to allow us to go back and forth. And the nice thing about this, of course, is that it has the exact same effect as the Fourier transform on that second order range derivative. Okay? So just like f, right, the Fourier transform, the Hankel transform, and actually let me put it in there, of the Hankel transform of 1 over r d by dr of r d by dr of that operator is going to be equal to minus kr squared. And let me just put in here whatever you put in there. Okay? I'd put in a dot. So in other words, in our case, right, the Hankel function of 1 over r d by dr, Hankel transform r d by dr of psi omega is going to be equal to minus kr squared psi omega kr, the transform, the doubly transformed pressure field now. If you want to prove this, prove by parts. All you got to do is integrate by parts. Same thing with that Fourier transform thing. And there's a nice reason why. And we'll get into that. And also note, just as an aside, the Hankel transform of the delta function r is just equal to 1. Well, that's going to be very handy with the right-hand side. So what does our wave equation look like? Well, after we transformed it, so it's all in there, we're going to end up with, we still have this z part untouched, right? So d by dz squared of psi omega kr, the doubly transformed pressure field. And now we're going to have k squared, right, from our Fourier transform, and we're going to have kr squared from our Hankel transform. And then on the right-hand side, we're going to have minus q over 2 pi. That delta r just became a 1. And now we have the delta z minus z prime. Okay? So actually, if this right-hand side was 0, we could actually pretty much write the solution to this, right? So homogeneous solution is well known, right? So it's going to be a summation, a linear combination of complex exponentials or sines and cosines, depends on, you know, some details of the problem. But basically, we could add as many of those as we like to the solution because they're homogeneous, right? But how do we deal with the inhomogeneous part? Okay, well, we need to transform again, right? Now we need to transform for the z part. Now, I'm sure you're looking at this and you're thinking right away, hey, that's the same as the t part, right? It's just a regular d by d something squared. But the difference is in time, our limits went from 0 to infinity, and in z, they do not, right? We have a waveguide that goes from 0 to h. So we need to transform that's over a finite domain. So we want to use a finite Fourier sine transform. Why do I say sine and not cosine? Well, okay, let's just do a little bit of simple physics here. We know that pressure is going to be equal to 0 here at the surface and at the bottom. And, you know, what is cosine 0 at 0? No, it's not. So let's just use sine and say, well, we're going to guess that for now, but yeah. And so for the finite Fourier sine transform, I'm going to use the same symbol here, but I'm going to put one of these. Oh, make it discrete. And here we're going to be going from z to m. The transform variable is going to be m, okay? So the definition of a finite sine transform, very useful thing. So now we're going to have the triply transformed field. So omega kr m. We're going to integrate from 0 to h, right? This finite limit. We're going to have omega kr. And the function is going to be sine m z over h and dz. Okay? The inverse is given by, so the one that brings us back to omega psi omega kr is actually going to be given by a summation. Okay? 2 over h sum m, oh, I'm too close to the bottom. M equals 1 to infinity. Okay? That's a 1 here. So an infinite sum omega kr m, same function, sine m pi z over h. Okay, and feel free to convince yourself that those are true inverses. Okay, but the question is, how does this act on that second order derivative, right? That's the whole, you know, the whole thing we wanted to get from these. So how does it act on d by dz squared? 3 question marks. Okay, well, let's, you know, we've said this a few times. Let's just try it out here, okay? If we integrate from 0 to h, kr over dz squared, sine m pi z over h dz. How do we do this? Well, I already gave the hint away earlier. We got to do it by parts, right? So we're going to do this by parts. And, you know, right away you can see that the idea here is that the sine, you're going to differentiate it twice and get back to sine. And you're going to integrate the second order derivative twice, and you're going to get back to psi omega kr. So by parts, you know, we say this is du, this is v. So u is equal to just the single derivative, right? So we get back a little bit there. And dv is going to be equal to m pi over h cos m pi z over h. So now we do by parts. We want uv first, right? So we have a single derivative. And then we're going to have this nice sine m pi z over h. And so right away you can see if we evaluate that at 0 and h, that's going to go to 0. Very handy. And then we're going to have minus, and that's actually, we've been neglectful here. Oh, no, we haven't. That's everything, right? Good. Okay. Then we're going to have minus, we had duv, now we're going to have u dv, right? So u, the integral from 0 to h, u is this dz omega kr, and then dv is going to have a cos m pi h over z, and I'm running out of room. Doesn't only happen on the board. And then let's put our m pi h out front here. Okay, so, well, we made a little bit of progress. We didn't get a solution, but it's quite obvious now that we need to redo this by parts, right? We need to go by parts again. Yeah, that's right. I have paper notes, of course. Take no chances. So in this case now, we're going to say same thing. This is going to be our du, and this is going to be our v. So our u is going to be very conveniently exactly what we're looking for, and our dv is going to be minus sine yada 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 with an m pi over h out front. Okay, chicken scratch, but at least it's something there. And so when we do that by parts again, we're going to wind up with a minus m pi over h all out front. We're going to have this guy here and a cos m pi z over h. Nice thing about this is we know that our function at the boundaries has got to go to 0. So that's going to go away. Then we're going to have a plus sign. When we add the minus sign there, we're going to have m pi over h again from the derivative again. We integrate from 0 to h. We have the thing that we want. We have a sine, which is great. This is looking very familiar. It's looking so familiar it hurts. And of course, this is in fact the actual definition, right? This is the definition of the transformed variable that we wrote on the previous page. So we're going to have a minus m pi over h, all that squared from the 2 bits here. And then we're simply just going to have the transformed variable, the triply transformed variable, right? Okay, so it works again, right? So the second order derivative, it brings out the square minus the square of the transformed variable. A little bit modified here, but it's great. It really simplifies things. So our triple transformed wave equation becomes, okay, well, we have our triply transformed pressure field, and then we're going to have our k squared, right, from our Fourier transform. We're going to have our kr squared from our Hankel transform, and then we're going to have our m pi over h squared from our finite Fourier sine transform. That's the left-hand side. On the right-hand side, we're going to have a q, we're going to have a 2 pi, we've got a minus sign, and now we need to figure out, okay, we've got the integral from 0 to h of this delta z minus z prime, and then we have sine m pi z over h dz. So what's the answer to that? You're screaming it out loud, you're waking up your roommates. Of course, when you integrate over the delta function, you just catch, it just catches at that prime variable, right? So we just get minus q sine m pi z prime over h, okay? So that's what we have on the left-hand side, or no, sorry, the right-hand side. Left-hand side, we have this super simple thing. Let's do something called algebra and simplify that equation. I'm trying something called sarcasm, you know? So that's going to look like this. Psi omega kr m equals, we're solving an algebraic equation. Wow, isn't this amazing? We used to have a partial differential equation, now we have an algebraic equation. This is why transforms are so awesome, okay? And I'm going to change some signs here. Let's make this plus here, and then I'm going to make this kr squared minus, oh sorry, plus kz squared minus k squared. I flipped the sign inside there. I changed it for the sign outside. Sine m pi z prime over h. Okay? You're like, wait a second, what the heck is kz? Kz is the vertical wave number, right? So we actually just had it as m pi over h. Now we're going to say that's kz. Okay? And we know what kr is. It's our horizontal wave number, and k, of course, is our wave number. So we solve this algebraic equation. This is our solution. Actually, I think it honestly deserves a box around it, because this is the solution. This is everything we need, right? We have what we wanted to find on the left-hand side, and we have an equation that defines it on the right-hand side, okay? But it's not in a very handy form. We're in a triply transformed space, and we really want to get something that's at least the solution to the Helmholtz equation, if not all the way back to P. So let's go back to P, or as close as we can. So how do we do that? We use our inverse transforms. Quite simple, right? It really is a recipe. We're just really just cranking the crank. So psi omega m. So we're going to start by invoking the inverse Hankel. So first, let's do this inverse Hankel. Okay. Well, we're going to have all the stuff that is not affected by the transform. Sine m pi z prime over h, right? This is all just constants out front. And then we're going to have the integral from 0 to infinity of kr, Bessel function, 0th order Bessel function krr, dkr. And all of that is going to be over kr squared, kr squared, plus kz squared minus k squared. Okay, what is that? Well, okay, I'm just going to write out the answer, and then kz z prime I pi over 2. Remember the Hankel functions that we looked at? This is the Hankel function of the second kind, 0th order, so some combination of Bessel functions, some special combination. Then we're going to have k squared minus kz squared r as the argument. So how did I get this? I'm going to just say that I did look it up. By definition / reference book / Wolfram alpha, right? There's a few different ways to figure this out, but really this is your Hankel function of the second kind, 0th order. And these things exist in MATLAB. These are, you should just think of them like functions as sines and cosines, Bessel functions. They come from series solutions, I guess. Is probably the most accurate thing. Okay, so that's given us psi omega m. Now let's inverse sine transform. Verse Fourier finite sine transform. So if you remember, the inverse was defined by summation, right? So all we have to do is simply just write our solution so far into that summation. So psi omega, right? We're going to only have, after we inverse this, we're only going to have a singly transformed field. It's going to be the solution to the Helmholtz equation. So we have IQ over 2h, and then we just had the summation, right? Now, it's an infinite sum, so that's not great, right? We don't really want to evaluate infinite terms because it's going to take us literally forever. But it's not too complicated looking a solution, right? So let's look at it. Let's look at it in a little more detail. Okay. Well, let's expand this into just something a little bit friendlier. We're still going to have this infinite sum, and I'm going to reorder. I'm going to switch the order here. So I'm going to say sine m pi z over h. That's our first term. Our second term is going to be sine m pi z prime over h. And our third term is going to be this Hankel function in range, k minus m pi over h squared r. Okay? So what are each of these terms, okay? Well, this is what we call the mode term. And it really describes the distribution of pressure. I mean, it really describes the depth dependence, right? Okay? Depth dependence. Now, it doesn't describe all of the depth dependence, but it's the only term with z in it, right? So I guess you need to sum over it and its products to really get the total description. But this term by itself, that has the depth dependence in it. What's this one here? This one has just the source depth, right? Z prime in it. And then you have to sum over all these modes, these signs, to get exactly how that source depth influences the answer. So we call this the excitation term. And the idea here is that it's all about source placement. So if you chose z prime such that that term was 0, then it would that whole term in the sum would be 0. Okay, so it matters. It really matters. And then what's this term in R? Well, this is the cylindrical spreading term, right? It's our only term that describes changes in range. And we need to take a closer look at it, right? So maybe when you were looking up what the Hankel function was in your book or in Wikipedia or in Wolfram Alpha, you might have also looked up the asymptotic. That was butchered. Asymptotic solution, which goes as, actually, let me just put this in generally here. For an argument alpha, this goes as the square root of 2 over pi alpha e to the minus I alpha minus pi over 4. Okay? So obviously in our case, range is in alpha. And you can see that, this is just a 2. It looks a little bit like an L. Okay. So how does this vary with range? Well, what's really important here is which term is dominating it. So if the first term is dominating, we're going to have 2 root pi, and then we're going to have, in our case, what's our argument? K squared minus kz squared r, right? So this is the first term, basically 1 over root r. So that's decay in the cylindrical wave, right? But what about this other term? So here it's going to be e to the minus I, the square root of k squared minus m pi over h squared r minus pi over 4, right? And so you're probably saying, well, there's an I up there, so it's oscillating, so it doesn't matter. But that's not always the case, right? So if this argument, square root, is real, then nothing happens. And you can just ignore this term. But if it's imaginary, well, then you get an I that comes out of it, and you get exponential decay, right? So let's write the second term here, as equal to minus the absolute value of kz squared minus k squared, right? So switch the order of the terms, and then r minus pi over 4, okay? And essentially we need this, so this is if k squared minus kz squared is imaginary. Okay? So really, this term is going to dominate if we have this inequality satisfied, right? So essentially, we need we have two different possibilities, right? So let me go to a new page here. It's going to be easier. I'm running out of room. Okay. So if we have m pi over h squared is larger than k squared, or simply m pi over h is larger than k, then we get the 1 over r decay, and second term oscillates. Okay? If this is not the case, otherwise, we get exponential decay. Much faster, kills the whole signal, right? Much, much faster. So essentially, this condition here, we say it allows modes to propagate. So the modes propagate. And of course, what is in that equation? Well, actually, k, right? Recall, k is omega over c. Can't say that enough times. So if we write this equation, this inequality really, we say omega over c is less than m pi over h. And we actually say, okay, what about 2 pi f? So let's say at the critical frequency. And what is the critical frequency? We're going to say it's the frequency at which modes, dividing the propagating modes and the exponentially decaying modes. Okay? Frequency fc. 2 pi fc over c, m pi over h. The pi's cancel. And we can actually solve for where the critical frequency is. And you can see that it depends on m, depends on c, and depends on h. So the mode number, right, the term in that sum that we're at, the sound speed in the water column, and the depth of the water column, okay? Now, so we said that we have exponential decay otherwise, so if f is less than fc equal to mc over 2h, then modes, or terms in the infinite sum, are considered evanescent. And, means exactly what you think it means. It means that they're there, but they're gone almost right away. They decay in range so quickly that they really don't need to be considered. Okay, so this is like a very simple, right? I mean, this deserves, this. This is a very simple little expression that tells us how many terms we need to include in our sum, right? So it's practically very important because we don't have to compute an infinite sum anymore. But it also is physically very important. It tells us how we can take our sound field and decompose it into a number of modes, right? And so we can also use it to compute the max number of modes, right? Okay. Predict number of modes at given frequency. And we just say m, now the capital M is going to be 2 pi f over c. So what do those modes look like? Actually, that is not correct. My notes are wrong. Let me go back. So what was our equation that we actually had? Is that not correct? Our equation was simply this. F equals mc over, that's right. Okay, mc over 2h. My notes are wrong. Wow, I should really change that so that never happens again. Now we want to solve that for m and say, so max modes m is going to be equal to 2hf over c, right? So that's going to be, important little tool there. So the real question is, what do these modes look like, right? So we're basically saying that our pressure field, right, and I'm just going to sketch it out here. It's an infinite sum. We had some sine m pi z over h. And then we had the excitation term. And we had the decay in range term, right? Obviously, I'm just being pretty, I'm roughing things out for you here. So, and then we made this little argument that was like, okay, we don't actually need to go to infinity. We can just go to the max number of modes for our frequency that we're at. And that's because for all the other modes that are outside of this sum, so a bunch of these decay exponentially, right? So that allows us to kick a whole bunch of terms out of our sum. And now we're just integrating from 1 to m, okay? Much more manageable. Sorry, integrating summing. So what are we left over with? Now we have this sine m pi z over h, and we have the excitation. So does that look familiar? I really think it does. If I were to tell you that we want to, we have slightly different boundary conditions here, but imagine now we have a string, and the string is vibrating between two fixed posts. I think it's very intuitive that all of you would tell me, well, okay, there's different modes that can fit on that string. It's, it's just basic physics, right? And that this complex waveform can be modeled as a summation of these modes, right? These finite number of modes. And that's really what this term is telling us here. We're decomposing the pressure field in range and depth as a bunch of depth-dependent modes, okay? And the excitation term is telling us, in the string example, it's basically saying, well, if you pluck the string in different places, you're going to get different modes that are excited, right? So if you pluck it very near the end, you're going to have modes with lots and lots of waves crammed into that string length. But you might have lesser low-order modes, for example. And so you have the exact same thing. You can place your source at a depth where it will excite some modes and totally not excite other modes. What's left over? This is basically just 1 to the r, so that's our cylindrical spreading, right? All the other terms went away when we dropped them out of our sum. And really that's what these modes are telling us, right? So we have our waveguide, pressure release surfaces, the depth is h, we put our source here at z prime, it's axially symmetric, it's range independent, and now we're saying, okay, we're going to have, this is going to be mode 1, 1, mode 2 is, going to be a total complete wavelength, mode 3, going to be, right, etc., etc. But there's another way to think about these modes, right? Really, this term here, or this depth-dependent term here, it's a vertical pressure distribution. It describes a vertical pressure distribution. In the sense that if we only had the second order mode and you put your sensor you put your hydrophone at the center of the water column, you're going to actually record nothing. You're not going to hear anything. Of course, that's not the case because we have other modes, right? So you're obviously going to pick up mode 3, and right. So depending on where you are in the water column, you're going to capture different amounts of different modes, okay? Now, why does that happen? Well, it's because there's interference, right? It's just a wave interference pattern. So this is the result. This vertical pressure distribution pattern is the result of interference of plane waves propagating up and down. Now, they're not just propagating straight up and straight down. They're propagating up and down at a certain angle. And that angle changes, it steepens as the mode numbers get higher and higher and higher, okay? Now, let me do a little toy problem to make that a little bit more clear. And this interference is all about satisfying these boundary conditions, by the way. That's what these plane waves are trying to do. I mean, that's what they have to do by the laws of physics. And it creates these interference patterns because of satisfying those boundary conditions, okay? So let me do a little toy problem to just make this a little bit more real, a little bit more intuitive, I think. I think it's going to help, okay? So imagine this 2D case where kx and kz are wave numbers. And here we're going to go back to our comfort of just plane waves. We're going to say we just have plane waves. We're just going to have plane waves in between two pressure release boundaries. Okay? So our field is going to look like this. E to the I kx times x plus kz times z minus e to the I kxx kz z. So we've got one going up, one going down, right? You see there's a minus sign here, going down, going up, okay? And we can simplify this. Turns into kxx times sine kz z, okay? You're going to use your Euler identities, and it actually is not, it's not too bad. Okay, now, when z equals 0, s equals 0, right? From that second term there. So the top boundary condition is satisfied. Now, what about that bottom one? Okay, when z is equal to h and s, so z equal to h, we're going to need s is equal to sine kz h equals 0, which is going to require us to make kz h equal to m pi, where m can be 0, plus or minus 1, plus or minus 2, dot, dot, dot. Okay? So, okay, when we invoke that, we get cos kxx and sine m pi z over h. Wow, that's exactly what we had from our recipe solution where we sledgehammered with a bunch of transforms, right? By exact, I mean it's just one mode, right? Okay, same mode shapes. It's not really exact. We derived. Exclamation mark. That's worth 3 exclamation marks, right? Okay, so that's very handy. Now let's say in terms of waves propagating with angles. These are plane waves. We started with some plane waves. They had some k, right? This was some k dot x at the beginning. What were the what's the geometry of that? Well, we know that we had, if we have k z upwards and kx is always going to the right, you're going to have some angle alpha, and then we're going to have k, the wave number, omega over c there, right? Some fixed length. So we know that kz is equal to k sine alpha, and that's equal to m pi over h. By the way, this little triangle, you remember from earlier classes, we said k is equal to the square root of kx squared plus kz squared, right? This wave number is equal to the hypotenuse created by the vertical wave number and the horizontal wave number, okay? Very handy little thing to keep in the back of your mind at all times, okay? So yeah, we have this relationship now between k sine alpha m pi over h. And so if we just simplify that, we can actually write, well, alpha, and now alpha is going to be indexed by m because it's discrete, right? It depends on which mode we're talking about. Inverse sine m pi over k h, okay? And this is basically telling us that each mode has a discrete grazing angle, right? So that gives the modal interference pattern, right? Because you have these fixed angles at which things can propagate. So gives modal interference. But it's also interesting in the sense that you can dump sound in certain angles and encourage certain modes, right? So it kind of links this purely vertical breakdown of the field into something that has a little bit more properties of the waveguide in it, I guess you could say. Certain modes. Okay, so quite an amazing little, quite an amazing little tool. What have we done now? If we go back here, so we've basically figured out a way to express the pressure field as a summation of modes. Okay, we started off though when we started doing that, we thought, right, when we went back here, we thought we were going to do the same thing that we did in our first, free field condition and in our, deep ocean homogeneous sound speed condition. We thought we were going to find what's called a wave number integral solution. And so the wave number integral methods are any methods where you're using transforms to solve partial differential equations. What did we actually end up with? We actually ended up drawing these modes, right? And we decompose the pressure field into those modes. And so this is called a normal mode solution. Now, of course, we chucked all those evanescent modes. If we wanted the true solution to the field, the actual totally unapproximated solution to this equation that we started off with, we would have to include all of those modes in our computation. But since we're usually far enough away from our source that those modes don't matter, those evanescent modes don't matter, our normal mode solution in an idealized waveguide is actually pretty good. So let's leave it at that. Next time, we're going to make our waveguide more realistic. That's our next step. So thanks for watching.